the maximum likelihood estimate of a binomial distribution. So here I am generating data um, from a negative binomial distribution, and the number of successes that we're seeking to obtain is 3. The probability of success on each Bernoulli trial is 70%. Okay, so this event is more likely to happen sooner rather than later. Um, so the number of failures that one would need to obtain 3 successes. So this would be 0 right here, and that's not the most likely outcome, but it's not unlikely. This is the second most common, which is just 1 failure. So that would amount to a total of 4 trials, whereas 0 would mean you have 3 trials exactly, and on each of the 3 trials you got a success. This would be 2 failures, so that would be 5 trials total. And the question is I plotted the negative binomial density with various parameters. So we don't know the probability of success. All that we have is this sample data. Okay, and using this sample using the sample data, we came up with this histogram for the number of failures. So the question is, which negative binomial distribution is most likely? So, um, you know, first of all, we're going to rule out uh, the 10% example, which is the one down here, and it has this color here, because the likelihood of observing this data is very unlikely, and it doesn't have the right shape. Okay. Now, the green one with 0.4, it would be more likely to observe somewhere around 3 failures or 2 failures than 0 or 1 with p equal to 0.4. So that's not very likely. That's not very consistent with the data. Okay. The red one's getting warmer, but um, but the issue here uh, is that the the 90% one, and more precisely this dashed one, which is the maximum likelihood estimator, are more consistent with the data. Okay, so uh, that's the maximum likelihood estimator visually explained, is that it's choosing the parameter here that is actually the most consistent with the data. And so, for example, we can rule out this 90% one because um, because the probability of observing 2 and 3, it's way more likely in the data than what the density function would imply theoretically. So that's not consistent. Okay. And so the question is, you know, uh, between this red one and this dashed one, and the dashed one's actually the maximum likelihood estimate. Here, having a large number of trials or number of failures is a lot less likely, whereas with the red one, we might expect to see something in 5, okay? Because that's not, you know, as close to 0 as the dashed one is. And that's why the dashed one is the maximum likelihood. It's more consistent across the board, okay? Now, this is a little movie we made, just showing the graph of the distribution versus the different parameter values. So this is p equals to 0.1. And the question is, what parameter should we choose for this negative binomial distribution that would have this same shape and be consistent with this data for this graph? So let's play it. Okay, so getting better as it increases, and then not so good. And the last one is the maximum likelihood estimator. So the goal is to find the parameter that is the most consistent. And it happens to be this red one here. That is the most consistent. Okay. So that's the maximum likelihood estimator in a graph. What about finding it with the calculations? Well, the probability distribution is given by this formula. Okay. And using maximum likelihood estimation, it says to take the product of the probabilities of observing all the data. So that's this thing right here. Okay. Our goal here is to estimate the probability of success. Okay. That's our goal. So we form this likelihood function. Then what we do is we take the log of the likelihood function. That changes products into pluses. And we get this. Keep in mind, we plug in r as 3, and it gives us this form. So this is the log of the likelihood. We want to maximize the likelihood function, so we take the derivative with respect to p, the unknown parameter. Okay. When we differentiate it, keep in mind that this first piece is a constant. P is the unknown parameter. We take the partial with respect to it. The derivative of log of p is 1 over p. The derivative of 1 minus p is 1 over 1 minus p times negative 1. And that gives us precisely this. Okay. Now all we do is we solve for p, that's just algebra, and it gives us this equation. That's our estimate here. So this says take the sample average number of successes, add 3 to it, that's what goes in the denominator, then 3 in the numerator. Okay, and you calculate that value. Okay, so that is the maximum likelihood estimator for the negative binomial. In the case, r is 3.